Howdy, y'all. I'm James.
Howdy, James. Howdy, James.
I think this is one of the last talks of PyTexas. It's Sunday, October 5th, 2014. This talk is called A CPython Eating Its Own Tail. This is one of my favorite presentations, and it shows you something that I think is actually legitimately kind of cool. Before I get started, I'll briefly introduce myself. My name is James Powell. The notes for this and some other really neat things you can do with Python are available on GitHub at gist.github.com/DUTC. That DUTC stands for Don't Use This Code. If you want to reach me by email, you can email me at james@don'tusethiscode.com. If you'd like to follow me on Twitter, which I'd much appreciate, I'm at Don't Use This Code. I have a increasingly less updated blog at seriously.don'tusethiscode.com, and I tend to camp on IRC on various channels like NYC Python and Python on Freenode as DUTC. Of course, the joke goes that DUTC is short for Dutch, and Dutch is short for Don't Use This Code, Haas. I actually got a laugh out of that. Great. Some of you may recognize me since this is the 10th PyTexas talk I've given. So maybe some of you know me already, maybe some of you don't. I'm the organizer. I'm actually the main organizer for a Python meetup group called NYC Python. It is the world's largest Python meetup group. We are 10 people shy of 6,000 members. We have events every other Thursday. We have large talk events with about 100 people every other Thursday, and we have weekly events, office hours, and study groups 3 times per week. The folks behind NYC Python, here's my goofy photo here and some of my amazing co-organizers. The folks behind NYC Python ran a conference this year in New York. It's called PyGotham. We ran it in August. I was the chair of that conference. It was amazing. The videos are available online. We had some really, really cool talks, and we're really psyched to do this again in 2015. Independently from NYC Python and independently from PyGotham, I ran my own conference in March of this year on Pi Day, March 14th, called For Python Quants. It was a conference targeting professionals in the analytical and quantitative finance fields. We had a lot of really cool talks. It was a one-day conference, and it was such a success that we are partnering with Paul Wilmot and TQF Institute and Fitch Learning to do this again at the end of November this year in London. And that talk actually is going to have the ability for people to interact online. So you'd be able to get an online ticket and actually ask questions and interact with the speakers. So I think it's going to be something really cool, and I'm really looking forward to it. So this is my third PyTexas. I'm really looking forward to having an opportunity to speak at PyTexas in 2015. Some of you may recognize me from PyTexas 2012 and 2013. I really like this event. I'm originally from Houston, and I always love coming back here. This is the 7th conference I've spoken at this year. We're right here. So if you're interested in the kind of stuff I talk about, you can probably Google my name and one of these different conferences, and I gave a couple of talks at each one of these. In my day job, I'm the managing director of a company called the Python Quants. I guess this cell didn't get evaluated, so you don't see the logo. We build analytical solutions for hedge funds, and we investigate the use of Python as applied to problems in quantitative and analytical finance. So I like to start these talks with a joke to warm up the crowd. I realized that the audience isn't mic'd for any of these talks. So if you're watching this talk online, I could say hello to the future. You can't hear any laughs from the audience, so either assume that the room is completely empty, my jokes are completely failing, or they're laughing, it's uproarious laughter, and you just can't hear it. So here's the first joke. How can you tell the difference between a chemist and a plumber? I actually like that one. That's pretty cute, huh? And I warned people in the talk that I gave this morning that I'm actually running out of these stupid jokes. I think over the number of talks I've given at PyTexas I've gone through more of them, and I'm not replenishing them fast enough. And I warned people, if I do run out of jokes, we're going to go to limericks, because that's another thing. I collect stupid limericks. And so I really like this limerick. It is a self-describing limerick. I will speak it as I put it on the screen. There once was an X from place B that satisfied predicate P. He or she did thing A in an adjective way, resulting in circumstance C. I really like that. I thought that's very clever. So I like self-describing poetry, and I like different ways that we can play with the medium. So let's get started. I like to start my talks with just an enumeration of themes. This talk is kind of the wild, wild west of Python. So one of the themes here is kind of an investigation of what Python is, how we can embed Python interpreters, and just the fundamental point is that it's really just all code. So the way that we think about Python, the way we think about a Python interpreter, the way we think about the distinctions between the system code that we write or the application code that we write, the platform code that we write, and the actual language and interpreter they're running on are actually very blurry. And maybe by deconstructing or maybe by dismantling some of these divisions that we put in our mind, we can produce code that has a smoother gradient between this code belongs to the language, this code belongs to the platform, this code belongs to the application, this code belongs to some plugin in the application. We could have a nice smooth gradient, and we don't have some of the problems when these layers interact or some of the problems that arise when we have unanticipated interactions between components in these layers. So this is the basic agenda that I'm going to go over. We're going to look at building CPython, running CPython under debugger. We'll talk about extension modules, the very high-level embedding, the pure embedding. I'll show you what I like to call the Cython embedding, and then we'll talk about a little thing I call Py3SO2. So let's get started with building CPython. So if we wanted to build CPython, if you were there for the CPython workshop we ran at 1 o'clock today, we went through these basic steps. We downloaded Python 3.4.1 from python.org. We unzipped it. We ran configure, and I passed a few debug flags just to make it more amenable to debugging under GDB. We did make and make install. Now, one thing that you might consider to be a little bit scary about IPython notebook is if I took out these comment characters here, it would actually do this entire thing in my IPython notebook. And that might be a little bit scary to actually do, a sudo apt-get install and making the files here. And then once we've built it, we can just use GDB to run it, and we can. One thing that we probably want to do is we want to source one of the tools that's provided in the CPython distribution that allows us to view rich details about some of the Python structures we have. So let me show you that in practice. So this is GDB with Python 3 running under it, and this is the build that we did earlier this afternoon. And all I have to do is type run, and here my program's running. And if I type Control-C, I've broken it into GDB. I can type BT to get a backtrace. If I were to source tools GDB libpython.py, when I do the backtrace, you can see suddenly I have full information about everything that's happening here. And if I were inside a function that took globals, actually you can see things like there's a file name, it's standard in. You see the repr for each of these objects. Depending on where I break, if I'm breaking somewhere where maybe a function is being passed a dictionary, I can see the content dictionary. It's really, really nice. So one of the examples, actually, let me show you. One of the examples that I'm going to use to motivate the rest of this presentation is an example that looks like this. And this looks a little bit abstract, but I want to press the point that there's a couple of points that it makes. What the example is we have a function and it takes 4 arguments. It takes 2 types and 2 values. It constructs one value using the type and the value, and another one doing that. So you can think that in use, this may look like this. I have 2 ints. One's 10, one's 20. I multiply them. The result is 200. I have a string 10 and an int 20, and I multiply them, and I get that string repeated 20 times. So let's see that live. So live, I'm saying I have, let me get my function here. I can just take this guy here, copy it into my terminal, and I can do int 10, int 20, and I get 200. And if I made this a string, I get a string that has the string 10 repeated 20 times. And this shows, this is the most fundamental, or this is the most basic example I can think of that demonstrates one of the topics that I think is very relevant to an understanding of Python and CPython, which is dynamic dispatch and how types are managed. And that we have no idea what the actual multiplication operation will do until we evaluate it at runtime, and the behavior of this operation can be wildly different depending on the types that are provided to us. And this has wide-ranging implications with regards to how fast our code can be or how we can optimize it, and also implications with regards to how we should structure our code to best make use of the facilities that Python provides us. It's also it's an example I picked because this talk was really motivated by somebody telling me, oh, you can't compile Python? And I said, maybe you can. And so this is the example that they used to show that you couldn't compile Python. And so it's the example I wanted to use to show maybe that's not quite correct. So in these examples, I'll either use that formulation or I'll use this formulation. This formulation is slightly different. Instead of just taking the type here. I get the type out of the built-ins module. I get the type out of the built-ins module. The reason for this is, in one case, I'm getting past these 4 arguments on the command line. So they're all getting pulled in as strings, and I want to just pull out these objects here. I'm not actually interoperating with this in a Python interpreter. So I'll show you this in play. Nothing too fancy, just mul, and I get string values for everything. Like that, and you can see if I turn this into that, a different result. So nothing too fancy here. The first thing I wanted to show you, and we looked at this in depth in our CPython workshop, was the dis module. And the dis module was my entryway into learning about Python, to learning about what was going on under the covers. The dis module provides you with a function called dis, and the dis function allows you to disassemble a Python code object. It allows you to see the code behind, or the byte code behind any Python callable. So let's do dis on our mul object. And we can do that. And we can kind of understand what's going on. In our code, we load global, or we load a function called getAttr. We load another function, or we load another global called built-ins, and that's a module. We load a local variable called type1. We call a function, which is called getAttr with these 2 arguments. Then we load another value here. Then we call another function, and we can kind of read through this and see what's happening. And the most interesting part of this, so all of this is the mechanics of kind of creating this value here and creating this value here. But in the end, what happens is we call this bytecode here binary multiply. So what I did when I started disassembling Python bytecode is I said binary multiply, I wonder what that is. And I kind of had some intuition of how you might write an interpreter. You know, I did some basic classes that talked about compilers and interpreters. And the way I thought, if you wanted to write an interpreter that was maybe a stack-based, opcode-based virtual machine, you might have some big for loop and some switch statement inside that for loop, and you'd have that for loop going forever. And in the switch statement, you'd switch on the various opcodes, and for each opcode, you perform some different action. And so I thought, maybe that exists in Python. So I grepped for binary multiply. And I ended up with these 5 results. And the first 4 results were, the first result is for a module called compile, or for a C file called compile. The second is for a C file called peephole. And I wasn't really sure what those were. But the last one was a file called ceval.c. So let's take a look at ceval.c. And in ceval.c, this is the line that binary multiply appears on. And if we scroll up, we'll find in this file a giant switch statement. And if we scroll up a little bit, we'll see that switch statement is inside a giant for loop that loops for infinity. So this is actually literally just our interpreter loop. And here we have the operation that performs our binary multiplication. Actually, it would be right down here. And if we were to chase this down, and we were to go into this function and see where does this go, we can see it leads us to a function that's implemented for all abstract objects, PyNumber multiply. And then that does some behavior to determine if you have 2 objects and they have the magic methods, that they have their underscore methods implemented, which one of the underscore methods do you call. And it also has some mechanism for determining what to do if one of the arguments is a sequence like a string. And if that's the case, it'll call sequence repeat. And so when we do that, we can actually investigate the operation of our Python interpreter in a very simple fashion. Let's just run our Python interpreter, Control-C to get back to GDB. We'll put a breakpoint. We'll put a temporary breakpoint at ceval.c 1486. That's the line where this happened. We'll continue running our Python program. We'll create 2 variables, and we'll multiply them together. And we'll see we've now halted execution of our Python interpreter right at the point before it's going to multiply these 2 numbers. And if we wanted to, we could step through this. And you can see it's stepping through the code. It's stepping through the code. And if we step into this, we've stepped into PyNumber multiply. And we keep going until we really understood what was going on behind the scenes. Now, there's one interesting thing that we can look at here. When I learned C way back in the day, we started by writing a main function. And I knew that the entry point for any C application is a main function. So I wondered, where is the main function for Python? And I could have grepped through a lot of code to try and find it. But I thought, if I have a program and it's paused at this point, I can just look at a backtrace of all the stack frames, right? And you can see, since I've used, actually, let me Oh yeah, I have. So since I've used this GDB, these GDB macros written in Python, you can see for this globals dictionary, I have a rich dictionary. Look how beautiful that is. I can see exactly what's being passed between these C functions if they're Python objects. But more importantly, I can see at the very end, number 10, that is my main function. So this is how Python works when you just write Python at the command line. It calls a main function in modules Python C, which calls pymain in modules main. And pymain calls runFile. And runFile calls pyrun, any file, x flags, and so forth and so on. And you can see for an interactive loop, we call pyrun interactive one object, and so forth and so on. And if we grep for what these are, and we want to investigate what these pyrun functions are, we can go into, these are in python run.c. We can see a number of interesting things here. We can see interactive loop, and we can also see pyrun simple file x flags. And so that's what happens when you write Python and then a script name. It'll call this function here. It'll load the flag, it'll load the code, sorry, it'll load the file, it'll load the code inside the file, and it'll execute the file. So with that, we should talk about extension modules. So we know that in Python we have modules that are not written in Python. Certain modules, like the math module, are written in other languages like C. In fact, a large number of modules in Python aren't actually written in Python. They're still written in C. Two of my favorite examples are the math module and the itertools module. The itertools module is a module that I tend to use quite a bit, and it's an example of how you can create rich Python objects using the C API. It's a module that's existed for a while, and if you are familiar with itertools, itertools has tools like chain from iterable, and you can see this is the chain object, and they've set up a struct, and inside the struct they have all of the different functions that get called when you instantiate the object, when the object needs to be garbage collected, when you call next on the object, when you call iter on it to get an iterable out. And this is just what a module written in C looks like. It's pretty tedious to write. It's mostly boilerplate, but this is what it looks like. I think the math module is also a very interesting example, because in the math module we can see that, let me go to sign. If we scroll to, I think, the bottom up here, we can see that we have a mapping between each one of the functions that were provided in the math module to some function that's being provided by the C standard math library. So this actually can't find it because that's created by, well, actually I think some of these are maybe created by macros these days. But you can see there's a general mapping and a little bit of shim code separating us between what we call from the math module and what's called in the GNU standard library. So that's all an extension module really is. It's writing a module in C, and we have access to some Python internals, and we don't have access to other Python internals. But outside of that, it's a little bit more boilerplate. We still have to manage some low-level details like garbage collection. We have to, if we want to create an object, we have to set up a struct like this. But outside of that, it's pretty routine. One thing that I thought was interesting is trying to figure out what is the entry point for the loading of a module. And it turns out that the entry point for a loading of a module is a function called pyimport load dynamic module. So what I've done here is I've started a GDB instance. I've put a breakpoint at pyimport load dynamic module. I've started running my Python, and we can see what's happened. Now let me source. So let me source tools, GDB, libpython GDB, and we'll do pname. And you can see this is my Python interpreter just starting up. It tries to load the readline module. And so here we have a hook. We have the area where a module is first evaluated. And if we look at this code, we can see some of the things that happen when a module is evaluated. We can step through this, and we can see at some point we have down, down, down. We'll actually, this is still a little bit of boilerplate. We add some objects here, and at one point here, we end up, oh, this is for loading a C module. So we basically do a lot of, we call dlsim to dynamically load the module there. So actually the point that I wanted to make was here for Windows and then otherwise here. And we dynamically load the module. We dynamically link against the module. Then we call a special function denoted in that module to initialize the module, which sets up all the initial state of the module, registers all the functions you have available, and then we return to the user. Pretty straightforward. So with that said, let's take a look at the very high-level embedding. And to motivate the very high-level embedding, let's think back to some of those pyrun simple string flag functions we saw. If we look through those, we'll see a function actually called pyrun simple string. And what this is a function that just runs a string. So if we were to start a Python interpreter and do a -c and give it a string like print hello, what this would actually do is pass this string to the Python interpreter and call a C function called pyrun simple string flags, and it'll just evaluate this down the chain just like it evaluates a file or evaluates code that's being input interactively via the interactive console. And that's really all the very high-level embedding is. So let me show you an example of the very high-level embedding. So the very high-level embedding looks something like this. This is a C program that embeds a Python interpreter using the very high-level embedding. And it embeds the program or the function that we saw before that multiplies two things together irrespective of whether they're two integers or a string and an integer or whatnot. And all it is I call pyinitialize to initialize a Python interpreter. I create the string with the arguments that I'm provided. Notice there's almost no error checking here. So there's almost certainly some overflow here. And I call a single function called pyrun simple string, and I call pyfinalize. Now notice a couple of things about this. One, I have no real ability to interact with the results of this calculation. I'm just running some code off in the background, so I'm not getting a return value here. And I have no way to interact with the currently running interpreter otherwise. I'm just telling it, here's a block of code, go run it as a black box, and maybe it'll have some effect, some side effect, but outside of that, I can't interact with that computation that's going along. I can't interact with the return value. Maybe it'll write to a file and I can read that file up, but within the program itself, I have very little interactability. This is, for example, if the usefulness of this is somewhat limited because there is no way to interact with it. But it's just a way that I can take a Python interpreter and just shoot it off and run a file and then get something back. So let's take a look at what I need to do in order to turn this into a program. Here's my makefile with all the examples for this talk. And for this one example, I just GCC with my very high-level embedding, and I link it against the Python libs. And I use Python 3 config in order to automatically provide me the libs that I need, but it's a pretty simple process. And here is the very high-level embedding in practice. If I press enter, you can see it tried to run this code here, and it was missing arguments. There were some nulls here, and so it blew up on me. But really, all I'm doing is constructing a string and evaluating that string. So if I type int 20 or int 10, int 20, you see what happens. If I do string, so it works. And all I'm doing is constructing a string and having the interpreter go off and evaluate it. Nothing too complex. Let's take a look at the next embedding that's discussed in the Python core documentation, the so-called pure embedding. When we put a breakpoint inside our ceval.c, inside our Python interpreter, we saw that a multiplication operation related to, or a multiplication operation corresponded to a pi number multiply operation. And around that we saw functions, or we saw bytecodes called things like binary power. And if we looked at that, we would have seen a pi number power. We would have seen a pi number add, a pi number subtract. And what we could infer from that is that for every bytecode or for every operation we can perform on Python objects, there is some corresponding C function that handles all of the dispatch and handles the execution of this. And you could think, if I took some lines of Python code, I know I can turn Python code into Python bytecode, because that's what the interpreter has to do in order to evaluate anything. And I know I could take that bytecode and I could go into my ceval.c and see which of those pi number or pi object calls that are being made. And I could probably just write those down. So I could take my bytecode and transliterate my bytecode into C code. And I could take that C code and I could compile it. And that would be essentially what the pure embedding is. So let's take a look at the pure embedding. The pure embedding looks something like this. It is exceptionally tedious. And what I have to do is I still have to do my pyinitialize to initialize my interpreter. And I have to create pi strings given C strings. So this program is a little bit better than the previous one. If I don't give it enough arguments, it complains, and I do a little bit of error checking here. But I just create Python strings from C strings. And I have to do this. I have to actually create a string to import the built-in module. Then I actually have to do the get attribute call myself. Then I have to create a tuple manually by creating a new tuple and setting the items of it. Then calling the function directly with this function pointer and this tuple. or this object and this tuple. And then I have to call PyNumber multiply myself. And you can see I'm just taking every step that would occur in that infinite loop with that switch statement and just writing it out. But one thing that I have here that's really nice is I can actually interact with the results. For example, here, I can print them out. I can print them out without having to have my Python code print them out, right? I could interrogate these results. I could check, is this value greater than this or less than that? And I might be able to add some modality to my code to say, well, if the computation that occurred in Python results in this value, perform this other computation in Python. And it could begin to, you might think, script your Python interpreter from C. But most meaningfully, what you can do is you can perform a Python computation in the Python interpreter directed by code written in C, and you can interact fully with the results of that, and you can interrogate the progress of that computation, and you can actually interact with what's going on in the Python interpreter. Unlike the very high-level embedding, where you're just shooting off some code, and it does whatever it wants. So, and you can see it's very tedious. I have to handle all of all the ref count incrementation and decrementation myself, and I have to finalize it myself. So let's take a look at that in practice. Here's our pure embedding. Here is our makefile for the pure embedding. And if we run the pure embedding, we can see it gives us, right? And if we do string, so it works. So we've basically rewritten this program. It works, and we've done another type of embedding. So these are the two embeddings that are covered in the standard documentation. I want to show you two interesting embeddings that I came up with. The first one is what I call maybe a Cython embedding. So we take this idea of you have some Python code, and that Python code gets converted to bytecode. And that bytecode gets run through this for loop that runs through the for loop and dispatches to each of these little blocks that runs some PyNumber function or some PyObject function. And it's deterministic, the correspondence between the bytecode and the C function. A binary multiply bytecode will always call a PyNumber multiply C function. And because it's deterministic, you could say, well, I can take Python code, and I can turn it into bytecode, and I can turn that bytecode into C code, and I could turn that C code into assembly, and I could take a Python class or a Python file, and I can compile it to assembly and just run it on a machine. And that's what Cython does. Cython is a transliteration, or that's the major thing that Cython does, is a transliteration from Python to C. And if you look at the code that Cython produces, outside of essentially a lot of bookkeeping that's necessary to actually make this work, that's really what Cython's doing. So I'll show you the process of what I call the Cython embedding. We start with this Python file. And all it is the function I was talking about before. We multiply two things together where the type of the two things we're multiplying is also one of the parameters of this function. And here's what my makefile looks like. I use this Cython command, or Cython 3, since I'm doing this all in Python 3, to take my Python file and to generate a C file. And this is what the C file looks like. It's horrible. You can see it's generated by Cython. It's impossible to read through. It's computer-generated code. But if you look through this, I know my function was called mul. So if I search for mul, I can kind of see, oh, here's the implementation of that function. Here's my prototype. And you can see all of the parameters that was passed, including a dummy parameter passed in order to adhere to one of the protocols of how module code is written. So you can see here's my type 1, my type 2, my value 1, my value 2. And here's a little bit of extra boilerplate. And if I search for this, I can actually see the implementation of this function. Here it is. And you can see it kind of looks like that pure embedding I just wrote. You can see it's getting a module name for the built-ins, it's creating pytuple new, it's doing PyObject call, and if I scroll down, I'm going to find my familiar PyNumber multiply. And other than being almost incomprehensible because it is computer-generated code and the variable names are really ugly and it's doing an enormous amount of boilerplate and a lot of other checks, this is essentially the pure embedding, an automatic version of the pure embedding. Now, one thing that I thought was kind of interesting was if we go back to this guy here, we'll see this static qualifier here. And you might wonder, what does the static qualifier mean in C? And for those of you who are C programmers and remember what the static qualifier means in C, it means a couple of different things in a couple of different contexts. In this particular context, what it means is a function is no longer visible outside of its compilation unit. So if I were to just remove this static qualifier, then what that means is I could compile this C file and I could link against it and call the function in the C file from another C file. So that's what I did. So let's look at this guy here. And you can see, It's actually somewhere down here. Oh, did I not remove the static qualifier? No, I did. Cython embedding.link. Well, maybe it's a, oh, it's a different, there must be a different one in here for the implementation of it. But, oh yeah, here it is. This is the one that actually does it. And I remove the static qualifier here, and if I diff the two files, you can see the only difference between the first file, the .link file, and the other file is that I've removed the static qualifier. Now, if I write a C program, and that C program puts the prototype for this function here, and does all the boilerplate to construct objects in the Python interpreter, construct a couple of string objects, I can now call this function in this automatically generated Cython code directly from a C program. And so once I build this, it's a little bit more complicated of a build process. I have to first compile my Cython module. Then I have to compile the module that I'm using in order to call into it. Then I build them together and link against Python, and I end up with this. This is a C program that's linked against the Python interpreter that runs Python code, not by intermediating through some other layer. It's actually running Python code transliterated to C. And one thing that we could think of is if we could withstand the tedium of it, instead of doing we don't need this PyInitialize, because we know how much memory this program is using. So we don't really have to initialize the garbage collector. We don't have to initialize anything. In fact, if we're not using any built-ins, we don't need this. Well, we don't really need to do PyUnicode from string, which will break if we haven't initialized the interpreter. We know that the PyUnicode object is just a struct. So we could just create a struct on the heap. And we could just fill in the elements of the struct. We don't need PyTuple new, because we could just create a tuple on the heap and just fill in the elements of that. And what we could do, if we were able to withstand the tedium, is we could actually write a little piece of code here that embeds a Python interpreter, but without embedding parts of the Python interpreter. We could actually compile Python without the Python interpreter. We could have a zero, what I called a zero-level embedding, where maybe you have an embedded Python that doesn't have a garbage collector, because now you have the complete flexibility to automatically generate C code. And once you have that flexibility, you can start trimming the fat. Of course, in order to do that, you have to be very careful, and it would be exceptionally tedious. But it's a possibility. And so that's what I thought was very interesting about this Cython approach. This is one of the other approaches I wanted to show that you actually can compile Python for many different meanings of compile. So with that said, a question came up. It was a question that lingered in my mind for a long time. This took me a couple of months to figure out how to do. I thought, I know there exists this thing called extension modules, and I know I can embed a Python interpreter into a C program in many different ways. Can I embed a Python interpreter into a Python interpreter via an extension module? Or in another fashion, there was an argument, I think back in the day, and somebody was like, oh, I wish I could use Python 3 because it's so great, but I have this one library and it's only available in Python 2, and I wish they would port it over. And I thought, well, if you could embed Python 2 into Python 3, then you wouldn't have to worry about the Python 2 versus Python 3 debate. You could just run the code that's written in Python 3 in the Python 3 interpreter, and the code that's written in the Python 2 interpreter in the Python 2 interpreter, and just find some way for them to interact. Unfortunately, it turns out that's impossible. So let's take a look at why it's impossible. Well, first, the global interpreter lock would give you all sorts of horrible problems. If you were to interact over that boundary, you'd probably have to very pessimistically lock on any access to these two objects. So if you accessed an object in Python 2 that might have been a bridge object that existed in Python 3, you'd have to lock both interpreters at the same time. So I guess that would be tedious, and it would slow down your program, but it wouldn't make it totally impossible. It would just be one qualification to what you had to do. You might have to worry about GC cycles. So if you took an object that was created by the Python 3 interpreter and passed it to the Python 2 interpreter, they'd both need to have a handle on that reference so that it didn't get garbage collected until neither of them were using it. But each interpreter could only see the objects that it had allocated. You could only see the objects on its own heap. So they wouldn't be able to see each other. So cycles between these two objects would be unresolvable. So you'd have to write a little bit of shim into the garbage collector. You have to write a little bit of code into one of the two garbage collectors to handle cycles between the two interpreters. So I guess that would be possible to do. It doesn't make it impossible. It would be possible to do. It would just be a little bit messy. And it wouldn't be that fast to do. You'd have to write some shims. So one example of the shim is There are embeddings of other languages into Python. Lunatic Python is an embedding of Lua into Python. And you have to write a shim very similar to what this does, which is, you can see, go to the end, this is just a shim that maps Lua objects, all the different parts of a Lua object, to all different parts of a Python object. So these different methods on a Lua object to different parts of a Python object. And you can see right here, they have, when you call string on the Python object, it ties it to, let's get this, it ties it to this guy, which actually calls some Lua code, and so forth and so on. So that would be something that you could do. It would take a little bit of time, and you'd be dependent on the interpreter version. You have to hope that nobody changed how a Pi object works, but that doesn't really happen. I mean, a Pi object is pretty stable over the life of Python 2 or Python 3. You'd have to wait till Python 4000 until that changed. So that would be a little bit more work to do, but it doesn't make it impossible. You might have to recompile everything if you did it by source filtering, but a lot of us compile Python in general. And maybe it's not impossible, but you shouldn't do it. It's a really, really bad idea. Don't embed Python interpreters into each other. So with that said, here's how I did it. The first approach I did was the most simplistic approach. When I tried to put a Python interpreter into another Python interpreter via an extension module, the problem I ran into was all the symbols matched. So they both had a pi number multiply function. And the compiler couldn't determine which pi number multiply function we're using. Symbol collisions all over the place. It blew up in my face. I took a weekend. I sat down. I used NM and object dump to figure out all the publicly exported symbols. I used sed to rewrite the names of all the symbols. I went into the code itself, and there's some places where functions were being generated by macros, and I patched that by hand. That's in the exception module. And I ended up with a custom build of Python 3, where every function had a py3. Every publicly exportable function and constant had py3 appended to the beginning of it. And then I was able to link it against a Python 2 interpreter, and I had a Python 3 interpreter running in a Python 2 interpreter. But it was really ugly because every single thing that linked against that Python 3 interpreter would have to be recompiled. And for the longest time, I thought there must be a better way to do this. But unfortunately, there is no better way to do it. There's no way that you can link the two together because the symbols will always clash. So source filtering is really the only way you can do it. So here's the way I did it, and here's something that I was looking at that kind of convinced me of that. If you go into Vim, Vim can actually embed both Python 2 and Python 3. And in Vim, you can tell it to use Python 2 or Python 3 for its internal scripting. And here's the code in Vim that does that. And you can see there's all these defines to take all of the different parts that are, or to add one layer of abstraction between the parts that are unique to Python 2 and the parts unique to Python 3, and to create one unique abstraction so that the rest of the Vim code base can refer to Python independent of the version. And if you look through this, you'll see there's one area here where they go through a for loop, and they just do DL open, they just do DLL lookups, and they just map things together. So they say, okay, I'm loading Python 2 shared object. Here's a struct representing all the parts of the Python interpreter I want to interact with. I'm just going to map, once I load it up, I'll just map the Python 2 pi number multiply to the pi number multiply I'm using here, and vice versa, and similarly for Python 3. So we have the same thing here. We're just doing all these mappings. And see here, they actually append everything with the Python 3, so they don't have symbol collisions, because both of these files get compiled into the same guy. And I thought, there's still got to be a way. Right? I mean, they seem to be getting a little bit close to it, but unfortunately, it turns out there really isn't. So here's an example of what happens when you try it. I used ctypes. I said, there's got to be a way to do this. Maybe in ctypes, I can use load library to load the Python 2 interpreter into my Python 3 interpreter. And I can get both of these two functions, and I can call them directly, and I can try and do something here. And when I run it, this is what happens. It blows up in my face. And the reason it blows up in my face is there's still internal parts of the interpreter that can't be disambiguated. And if you go into GDB and you try and figure out where the problem is, there's just there's utter confusion as to what you're looking against. There's still collisions. It's unfortunately just really not possible. So I thought, what if I use raw DLSim instead of using ctypes? So I tried that as well. And it looks something like this. It's very similar to the ctypes approach. But I use raw DLOpen, and I use raw DLSim, and I try and initialize my Python 3 interpreter, and I try and initialize my Python 2 interpreter. And I'm not even initializing them within each other. I'm just initializing them in parallel within the same C application. So I try that, and I get another ridiculous error. When the Python 2 interpreter tries to initialize, it tries to manipulate some structure that it thinks is its own, but it's actually confused with the structure that Python 3 has a handle on, and it just blows up in your face. It just doesn't work. And if you go onto the DL Open man page, you can see there are all these different flags. And if you scroll down to here, you'll see there's really no way to embed two Python interpreters into the same process, because you will never be able to disambiguate all the things that, you'll never be able to figure out the linking problem. If you scroll down to here, you'll figure out how I actually did it. So here's how I did it. Use RTLD deepbind, and this I think is really cool. I really love this. So it's the exact same program, and I just pass one more flag to DLSim called deepbind. And what deepbind says is, you take a shared object and you load it. And when you're disambiguating a symbol, you do not take the symbols in the object that you've loaded and put them into any scope other than themselves. So when you go into that Python interpreter and you tell it to initialize itself, all the calls in that Python interpreter that reference some symbol will only ever see symbols within that shared object. And when you pull in the other Python shared object, all the symbols in that Python, or all the functions in that Python shared object will only see symbols in that Python shared object. And so they're completely separate. And so here you have two Python interpreters running within the same C process. You have a Python 2 and a Python 3, both running within the same C process. And let's take a look at what this prints out. There's nothing up my sleeve. It prints out version info, and it prints out the process ID. So both of them print out version info and the process ID using Pyron simple string flags. So you can see that's the version info of one of them, the version info of the other one, and the process ID. And they're both the same. So we have two Python interpreters running from within the same C process. But that wasn't really enough. I kind of got bored at that point. So I thought, well, maybe you could run multiple Python interpreters. So here you can see, instead of instantiating one Python interpreter, I instantiate an array of Python interpreters. So here you have two Python 2 interpreters and two Python 3 interpreters running within the same process. So here you go, two Python interpreters and both. There was one limitation to this, which is DL open will not let you open the same shared object twice. If you try and open it again, it'll give you a handle to the one you already opened. And the workaround for that is you just make a copy. As long as it's a separate file, you make a copy. There's one other workaround that I'm still trying to find the time to do, which is if you patch your linker so that your linker will allow you to load the same shared object twice, then you can get this to work. In which case you could run 10 Python interpreters within the same process, which would be really interesting because you could give them all a handle to the same piece of read-only shared memory, and you could implement multiprocessing without having to worry about process boundaries for passing memory around. They could all see the same memory in the same process space. You'd pay no penalty for copying memory across a process. And you could potentially interact, but you'd have to be very safe about interacting. But if there were read-only memory, you could actually have some kind of concurrency approach that you did with kind of like multiprocessing, but multiple Python interpreters running right side by side without interacting with each other. So that's that in practice. And one thing I thought was, how can I use cffi to embed the Python interpreters into themselves? Because that's what I really wanted to do. So here's actually an implementation of, I was on a flight. Once I figured this out, I was on a flight afterwards, and I thought, Python 2 and Python 3, maybe we can go one more. So on the flight, I had the source code for Python 1.5. And I decided to build a shared object with Python 1.5. And I was really surprised. Apparently nobody's done that before, because the Makefile didn't have the targets for building a Python 1.5 shared object. So I hacked for like 30 minutes or an hour, and I was able to build a Python 1.5 shared object. And I decided I didn't want to write any C for this. I wanted to write all of this in pure Python. So here we have a pure Python, well, except for the libraries that themselves written in C. But here we have, as our deliverable, a pure Python file that uses cffi to embed a Python 1.5 interpreter, a Python 2 interpreter, and a Python 3 interpreter all into the same process space. So here's that running. And you can see we have 3 interpreters running within the same process. They're all, this is the PID for all of them. And you can see Python has matured a lot over the years. You can see back in the 1.5 days, version info was just a string. And now it's this beautiful little rich object here. And you can see we have 3 Python interpreters running simultaneously within the same process space. And so the last example is this, where, oh, that's actually the last example. So I thought those were some interesting approaches. I'm glad that I had an opportunity to share this with you. This is my example of CPython having eaten its own tail. There's still a lot of work to do. For example, if you wanted the interpreters to interact with each other, you'd have to go ahead and write those shims. And those shims would have to be GC aware. They'd have to be global interpreter lock aware. if you wanted the Python interpreters to run inside of each other, if you wanted multiple Python interpreters to run without having to copy shared objects around, you'd have to patch your linker, and that turns out to be kind of difficult to do because you have to find the hook in the linker for where it you'd have to find a nice way to hook into the linker so that it would allow you to load the shared object multiple times. And in practice, that's taken me more than a couple hours to do. But you have to maybe spend a week figuring that out. And then you'd be able to run Python 2 and Python 3 in the same process without writing any C code. And I guess your coworkers might hate you, but I would love you. So that's my talk. I hope you enjoyed it. And I'm really glad to have been able to participate in this conference, and I'm really glad I had an opportunity to present this in front of all of you. Thank you. So, please.
Is there any sort of basic level binary compatibility between the versions that you found when passing around PyObjects?
So the PyObject structure has changed slightly between Python 2 and Python 3. Certain things have also changed, like some built-ins have changed. You no longer have string built-ins in Python 3. You only have the Unicode built-in. You really just have to write a shim. You'd have to say, well, when you call the Python 2 TP-init, that just kind of in the background calls the TP-init equivalent on the Python 3 object. And it would be mostly tedious. It would look very similar to this Lua bridge. It would just be a bridge. And the maintenance of it would be very minimal because Python 2 PyObject API, or ABI, or whatever you want to call it, doesn't really change. I mean, it's static for all of Python 2. Were there any other questions? Don't ever actually do this. That's a really terrible idea. But I thought it was interesting. I thought it was fun. Okay, thank you so much.